This lesson is on inertial navigation system errors. Firstly, we need to remind ourselves how the information flows in the INS in order to work out what the sources of error will be. The accelerometer is mounted on a platform which is stabilized and north-orientated by gyroscopes. It detects accelerations, which are passed to the first stage integrator. Here they are integrated into velocity. One feed of this velocity is taken forward to the second stage integrator, where it is converted to distance gone and added to the present position, thereby generating a new present position. A parallel feed of the velocity is fed backwards through a V/R feedback loop, where it is converted to the omega term, which is used to rotate the gyro to keep the platform perpendicular to the local gravity vector. The same sequence is taking place simultaneously in the east channel, the only difference being the addition of a secant multiplier to convert the easterly distance gone, or SE, into change of longitude. So, where are the possible sources of error? There are 6. We'll explain them in more detail in a moment, but first we'll list them. These errors are platform tilt, accelerometer bias, integrator error, leveling gyro topple, initial azimuth misalignment, and azimuth gyro drift. Let's start at the beginning. Firstly, the platform may not be perfectly level. Platform tilt can also be known as initial leveling misalignment. The leveling process during alignment is very accurate. Ideally, it should be within about 6 seconds of arc. This is 1/600th of a degree. Nevertheless, it is a compromise with the requirement for a reasonably short alignment time. On completion of the alignment, the platform may not be perfectly level. Accelerometer bias is next. The accelerometers are designed to give 0 output for 0 input, if properly leveled. However, due to manufacturing imperfections, there may be some slight output when the accelerometer is perfectly stationary and level. This is called accelerometer bias. Next, we'll look at integrator error. For a 0 input into an integrator, there should be a 0 change of output. Again, due to manufacturing imperfections, there may be some slight scaling error. Taking the second stage integrator as an example, suppose the velocity input were exactly 400 knots for exactly 1 hour. If the distance gone output to the present position display were 401 nautical miles instead of 400, that would be an integrator scaling error. Integrator error can be present in both the first stage and the second stage integrators. The next error to consider is leveling gyro topple. We said that the platform and gyro might not be initially perfectly level. However, the gyro may also topple from its start position. With the accuracy to be expected of IN quality gyros, the topple rate would be of the order of only 1/100th of a degree per hour. But nevertheless, it is finite and would have an effect on the output. Apart from leveling, there is also the heading output to consider. Horizontal direction is called azimuth, so this error is called initial azimuth misalignment. Gyro compassing usually results in an initial alignment accuracy of about 0.1 of a degree. This is very accurate compared with a gyromagnetic flux valve heading, but even 1/10th of a degree introduces appreciable errors. Finally, there is azimuth gyro drift. In addition to any initial misalignment error, the azimuth or heading gyro may also drift. This drift rate would typically be of the order of only 1/100th of a degree per hour. But as with the topple, it is finite and would have an effect on the output. So this comes to 6 input errors, or 7 if we split the integrator error into first stage and second stage integrators. We are now going to see what effect they have on the output data. The first error we're going to look at is platform tilt. But before we do, we need to modify our diagram slightly. We shall want to see what effect these errors have on acceleration, velocity and position. The basic pattern is unchanged. We still have an accelerometer on a platform. The output is acceleration, but this time we've put an imaginary meter in so that we can see what's happening to the acceleration. With the needle at the 12 o'clock position, that means no output. If it is over to the left, that means a positive acceleration. If it is over to the right, it means that there is a negative acceleration. The acceleration goes to a first stage integrator, where it becomes velocity. The velocity goes onwards to the second stage integrator. But again, we can monitor it with our next imaginary meter. And again, vertical means zero output, left means positive, and right means negative. Here's the second stage integrator, with its output of distance, for which we used the same convention. It's just easier in this diagram to see a needle presentation than changing digits for latitude and longitude. Finally, there's the V over R feedback loop. And here is the gyro. So now let's see what effect is caused by an initial levelling misalignment or platform tilt. Imagine that we are on the ground, alignment has just completed, and we switch the MSU to navigate mode. Here's the basic diagram. But unfortunately, on completion of the alignment, there is some levelling error. The component of gravity will be misinterpreted as a false acceleration. So let's show this false acceleration on our meter. This acceleration will be passed to the first stage integrator, where it will be integrated into velocity, and then to the second stage integrator, so that it will be integrated into change of position. At the same time, the velocity is passed back along the V over R feedback loop. The system can't tell that we are still on chocks, and this is a false velocity, so it assumes that the aircraft is travelling around the curvature of the Earth, and slowly brings the platform to the level, which means that the source of the false acceleration is removed. You might think that this has solved the problem. The platform is now level, and there is no false acceleration. However, it hasn't. We have a build-up of velocity. The way that an integrator works is that if you have zero acceleration going in, it doesn't mean that you have zero velocity going out. It means that you have zero change of velocity. Therefore, the velocity continues to be passed to the second stage integrator and to the position display, displacing the position further. And it also continues to be passed back along the V over R loop, thereby rotating the platform as far over in the opposite sense as it was at the start. So the acceleration is now negative. This will become a negative velocity, which will be integrated to reduce the distance error and fed back to bring the platform back to the level. However, we still haven't finished. We still have a velocity in the system, which will be fed back to drive the platform to its original position. So the system is now in precisely the same configuration as it was at the moment of selecting Navigate. The whole loop has oscillated one full cycle to return to its initial configuration. It will continue to oscillate in this manner until the INS is switched off. We have had an apparent change of position and then a return to the original position, even though the aircraft has not actually moved. This type of periodic error pattern is called a Schuler oscillation. This is the Schuler pattern of error caused by platform tilt. It is sinusoidal in form. 2 cycles of oscillation are shown in this picture, but in practice the oscillation will continue until the INS is shut down at the end of the day. The distance error starts at 0 at the moment of selecting Navigate, then increases to half of its full displacement after a quarter of a cycle, reaches its fullest displacement at the halfway point of the cycle, then reduces back to half displacement at 3/4 of the way through, and finally reduces to 0 at the end of the cycle. Each cycle takes 84.4 minutes. This never changes, because it is based on the constants in the V/R feedback loop. These are the value of gravity and the radius of the Earth. Therefore, it does not matter whether your INS was designed by Honeywell, Delco, Lytton, or anyone else. It will have to have a V/R feedback loop to keep the platform level as it travels over the Earth. And if the platform is not level at the start, there will always be an oscillation with a period of 84.4 minutes. This is called the Schuler period. The maximum value of the Schuler error does not increase with time. Whatever the amplitude of the first cycle, all subsequent cycles will have the same amplitude. The oscillation is self-sustaining, because the system is resonating at its natural frequency.